Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and this is Astronomy 3450, Mission to Mars, Lecture 4, Orbits, Part 2. In Part 1, we studied Kepler's laws of planetary motion. Kepler discovered the basic properties of orbits by studying how planets orbit our sun. You'll remember that Kepler discovered that all the planets orbit on ellipses, that when a planet is closer to the sun, it moves faster, and when it's farther from the sun, it moves slower. And then he discovered that the squares of their periods of revolution are in proportion to the cube of the semi-major axes of their orbits. Now, what's important about Kepler's laws of planetary motion is that they don't just apply to planets. They apply to orbits of all kinds. They apply to planetary orbits. They apply to the orbit of our sun around the center of the Milky Way galaxy. But most importantly for our course this semester, they apply to satellites orbiting the Earth. So Kepler's three laws also apply to satellites. In terms of satellites, all satellites orbit on an elliptical orbit. When a satellite is closest to the Earth, it's moving fastest, and when it's farthest from the Earth, it's moving slowest. And we learned at the very end of our last lecture from Newton's modification to Kepler's law that the semi-major axis cubed of the orbit is proportional to the period squared times a number of constants. In this lecture, we're going to talk about orbital elements, how it is that we specify an orbit, and then we will also talk about the different types of orbits and their uses. So imagine that I have a satellite in orbit around the Earth. What numbers do I need to specify so that its orbit is precisely and exactly determined? Well, you can imagine that the first thing I need to do is specify a day and a time, an epoch as we call it. See, the orbital elements that we publish are a snapshot in time of what the satellite is doing. It's literally one moment in time what the orbit looks like. And the reason for that is that orbits are constantly evolving. They're changing over time. Spacecraft can maneuver, or even through natural causes, orbits will, as we will see, precess and can change. And so when we specify the orbital elements for an object, we're talking about what they were at some specific moment in time. And that moment in time, we just specify a day and a time, and that is the epoch of the orbital elements. Then the other three things that we need to specify for the orbit are the shape of the orbit, its orientation in space, and then finally where the satellite was located inside of its orbit. So let's talk about how we do those last three. How do we specify the shape of an orbit and its size? How do we specify its orientation in space? And then how do we specify where the satellite was located? Well, when it comes to shape, you're already familiar with that one from the last lecture. When it comes to the shape of the orbit, there are two numbers that we need to know. We need to know the size of the orbit, and we specify the semi-major axis. So the semi-major axis is half the major axis of the orbit. And then we also need to specify the eccentricity of the orbit. So here's a really nice diagram that just shows us an elliptical orbit, and it shows us here's an orbit around the Earth. So here's the perigee, the point where the orbit is closest to the Earth. Apogee, where it is furthest from the Earth, right there. And then the two numbers that we need to specify the shape are the eccentricity. You'll remember the eccentricity runs from 0 to 1. An eccentricity of 0 is a perfect circle. A small eccentricity is a near circular orbit. A high eccentricity is a very elliptical orbit, and an eccentricity close to 1 will be very long and thin. And then an eccentricity of exactly 1 defines a parabola, which is not a closed orbit. That's an object that will not return back. To specify the size of the orbit, we specify the semi-major axis. You'll remember the major axis is the distance from the perigee to the apogee. It's the distance across the long axis of the ellipse. The semi-major axis is simply half of this. And the semi-major axis also works out to be the average distance that the satellite has from the planet or from the sun or from whatever it's orbiting. The semi-major axis is also equal to the average distance. And you can get that because you'll remember the argument from the last lecture that if we know the distance when it's closest and we know the distance when it's farthest, well, the average distance is just the average of those two. It's the average of the closest and the farthest. Well, to take an average of two numbers, we take a plus p divide by 2. In this case, we take the perigee distance, add on to it the apogee distance, and divide by 2. Well, the apogee distance plus the perigee distance is simply the length of the major axis. Dividing that by 2 gives us half the major axis, or the semi-major axis. So that is the second number that we need to specify the shape of an orbit. Now, down in this corner is a really neat little diagram that shows you two objects orbiting. They have exactly the same orbital period, but one is orbiting on a circular orbit and one is orbiting on an elliptical orbit. And a couple things that you can see if you watch that animation for a few seconds is, first of all, they have exactly the same period. So the two of them, when they get down to their perigee point, in this case, lines up over here, you can see that the two of them line up. They also line up, as you saw just a second ago there, at half the period. You'll notice Kepler's second law at play here. Watch this one. As it comes into perigee, it will move faster. And the two of them catch up and they're exactly lined up there. And because they have exactly the same period, they will come right back together again. They will also line up at half a period. You'll notice that this one reaches apogee at the same moment that this one reaches over here. But it's kind of neat to see Kepler's second law at play there, where you can see that in this case, because it's moving so slowly, the circular orbit gets ahead of it. And it looks like if these were in a race that the circular orbit was going to win, but because of Kepler's second law, as this one falls in, it moves faster and faster and it catches up so that ultimately the two of them reach the starting line at the same time. Now that starting line in this case points right to the perigee. It's a line that goes from the focus that has the main body out to the perigee right there, and we call that the line of the line of periapsis. So the line of periapsis is the line that connects the center of the Earth to the perigee point. The true anomaly is just a measure of the position of the satellite in its orbit. So we'll get to this a little bit later on, but I just want to mention it now because I thought this was a really good diagram for pointing it out. The true anomaly tells us where the satellite is in its orbit. A true anomaly of 0 degrees tells us that it's at periapsis, or in the case of an Earth orbit, perigee. An angle of 90 degrees would tell us that it's at a right angle to the line of periapsis. And a true anomaly of 180 degrees tells us that it's at apogee. An angle of 270 degrees tells us that it's once again at a right angle to the line of periapsis, and then an angle of 360 degrees brings us right back to periapsis or perigee again. So that's the true anomaly, and the true anomaly down here tells us the location of the satellite. So we've talked about the semi-major axis, the eccentricity, and the location of the satellite. Now we need to talk about the orientation of the orbit in space. So how are we going to do that? There are three numbers that are needed to specify the orientation in space. And the first of those three numbers is the inclination of the orbit. And the inclination of the orbit tells us how much the orbit is tilted with respect to the Earth's equator. An inclination of 0 degrees is orbiting right above the equator of the Earth. An inclination of 90 degrees is orbiting over the poles of the Earth. So that's something that it's worth memorizing. Inclination of 0 degrees is on the equator. That is, it's orbiting right around the equator. And inclination of 90 degrees is orbiting around the poles of the Earth. So that is the orbital inclination. And you can have an orbit that's anywhere in between those two. Now, most orbits are inclined, other than geostationary orbits, which we'll talk about later on in this lecture. Typically, an orbit is inclined to the Earth's equator. So this white plane right here defines the Earth's equator, which is basically the Earth's the plane that includes the Earth's equator. And the satellite can be above the Earth's equator and below the Earth's equator. So here's an example of it right down here. So we've got the Earth's equator right here, and then we've got the satellite orbit, and it is inclined by some angle to the equator. If it's inclined by some angle to the equator, there's a place where it crosses the equator going up and a place where the satellite crosses the equator going down. And we call the place where it crosses moving upwards, when it's moving from south of the equator to north of the equator, we call that the ascending node. And then, as you can guess, complementary, on the other side, when it is descending, going from north of the equator to south of the equator, we have another node, and that is called the descending node. Now, when it comes to specifying an orbit in space, the ascending node is the important one right here. So the ascending node is the one that we need to understand. So remember, that's where the satellite goes from south of the equator to north of the equator. Just as it crosses the equator, we call that point the ascending node. Okay? So that's the inclination of the orbit. The last two numbers that we need specify how this orbit is oriented in space. And I think the easiest way to show that is to actually bring up a little tool that demonstrates this kind of nicely. And so what I've got here is a little tool from orbitalmechanics.info. So I've got the Earth right here, and this orange plane defines the Earth's equator. You'll notice that orange plane is cutting the Earth almost exact, well, it is cutting the Earth exactly in half, to the northern half and the southern half. That is, that orange plane corresponds to the Earth's equator. Now, the first number that I need to specify is the semi-major axis, and that defines the size of the orbit. And there's a nice little slider here, and I can define the semi-major axis in terms of the Earth's orbit, in terms of the Earth's radius. Now, here's the thing. Most satellites that we think about are at very low orbital altitudes. That is, their orbital radii compared to the radius of the Earth is quite small. Let me give you an example. The International Space Station, the orbital radius is 1.066 Earth radii. So that would be, if I get that right there, let me see. There we go. So that's the International Space Station right there with an A, a ratio, an orbital size that's 1.066 times the radius of the Earth. So in order to see that, we'd actually have to zoom in here. And you'll notice you can see the gap between the surface of the Earth and the International Space Station there. But it gives you an appreciation for how low the International Space Station is, or how close it is to the Earth. And in fact, as we'll see, this is true for most objects that are in low Earth orbits. The second thing we need to specify is the eccentricity of the orbit. So let me zoom out a bit here. And so we can have various eccentricities. Let me change this a little bit so that you can see the eccentricity a little bit better. So you can have an orbit that's very eccentric, an orbit that's not very eccentric. Now, the problem when you're very close to the Earth like this is you cannot have a very eccentric orbit, or your satellite will crash into the Earth. So just for purposes of making it easier to see, let's zoom out a little bit. Let's make the orbit much larger, and now we can see an eccentric orbit. So here's an eccentricity of about 0.8 right there. So that's a very eccentric orbit around the Earth. As I said, an eccentricity of 0.8 for an orbit that's about 6 times, we'll make it a nice round, 6 times the radius of the Earth. So those two numbers, the size of the orbit and the eccentricity, specify the shape of the orbit. Now we need to specify its orientation in space. So the first thing we're going to specify here is the inclination, how it's inclined. And so I can tilt this orbit here. So we can have an inclination between 0 degrees, which is over the equator, all the way up to an inclination of 90 degrees, pretty close to exactly 90 there, which is an orbit over the poles. We can even go over the top and have an inclination that comes all the way down to 180 degrees. So that is the inclination. So I'm going to stop this one here. Let's stop this one at about 60 degrees. So there's an inclination of about 60 degrees right there. The last two numbers that we need to specify tell us how the orbit is oriented. Now, I don't want you to worry too much about these numbers. If you get into someday working for a company that operates satellites, you'll have to understand these in great detail. But for right now, just know that the two numbers are called the argument of the perigee and the argument and the right ascension of the ascending node. So let's take a look at our orbit right here. So we've got our satellite going around. Our ascending node is right over here. So let me let's see, change this a little bit this way so that we can see this a little bit better. Okay, so here's our satellite going around, and you'll remember it dips way below the Earth and then it's coming back up. Right over here on the right-hand side, we have the ascending node of the orbit. The argument of the perigee simply determines how that is located in space. So you'll notice this little arc right here. This arc tells us the argument of the perigee or the argument of the periapsis. If it's 0 degrees like that, or close to 0 degrees, I should say, it lines up with the perigee point. And then as we shift it around, it shifts the orbit this way in space. So it determines the orientation of the orbit this way. So you can play with this if you want, just to see how it shifts it around. If I turn it a little bit this way, you might see a little bit better what's going on. So now you can see that argument right there just shifts the position of the orbit. So how that orbit is oriented around the Earth right there. The second one is the right ascension of the ascending node. And you can imagine if we're tilting the orbit this way with the argument of the perigee, the right ascension of the ascending node is going to swing it around in a different direction. And so that swings it around this way. So those two numbers determine how your orbit is located in space. Now, the right ascension of the ascending node, right ascension is measured with respect to an arbitrary point in space. Astronomers thousands of years ago picked a point in space to be sort of the origin of the sky, the zero coordinate position in the sky. And that is where the Earth's equator meets the Earth's orbit around the sun, where the sun is located on or about March 21st at the vernal equinox. It's called the vernal equinox point, and that's the origin in the sky. And all the right ascension of the ascending node measures is the position of the orbit with respect to that position in the sky. So 0 degrees means that the orbit is pointing right at that 0 point in the sky, and then you can switch it all the way around, all the way up to 360 degrees, so the orbit can be oriented any way in between. So that is the right ascension of the ascending node. It's twisting the orbit this way, and the argument of the periapsis, or the argument of the perigee, is swinging the orbit around this way. So again, don't worry too much about those last two if you don't quite get them. Just know that they specify the position of the satellite in its orbit. So they specify where the satellite is located in its orbit. They specify how the orbital plane is oriented in space. So let me give you an example of one of these orbits, and let's do this for the Chandra X-ray Observatory. So the Chandra X-ray Observatory is a major X-ray observatory. Now, its semi-major axis is actually 12 times the Earth's radii, and I can't do that here, so all I can do is I can make it 6. That's the maximum that I can do. The eccentricity of the orbit is about 0.8. The inclination is about 57 degrees, so let me change this to make that right around 57 degrees. And then at a particular day and time, it actually happened to be for the day that I'm recording this, W right here, the argument of the periapsis was 226 degrees. So 226 degrees, about there. And then the right ascension of the ascending node was actually about 260 degrees. So that's about, 260 or so right in there. And then the mean anomaly, where the satellite is located in its orbit, was actually almost exactly 0 degrees. So that the moment that I got the orbital elements for, the satellite was actually at perigee. It was at its closest to the Earth. And so if we zoom in on a little bit here, you can see that the orbit of this satellite comes very close to the Earth, and then it comes quite far out, and then very close to the Earth again. So that's an example of the orbit of a particular satellite. Okay, so here's another diagram that tries to show these a little bit better. I'm not sure that it helps very much, but you'll remember that the argument of the periapsis is the angle between the ascending node. So we've got this body, celestial body, that's in orbit right here. So we're just going to they call it a celestial body. We're just going to call it a satellite. It's a satellite in orbit around the Earth. So here is the ascending node. This is where the satellite is going from south of the equator to north of the equator. And then this is where the descending node over here. The important one is the ascending node. And the argument of the periapsis tells us that this is the perigee point when it is closest to the Earth. And this angle right here, called the argument of the perigee, just tells us where this is located with respect to the ascending node. So again, if this was 0 degrees, that would mean that the perigee point also coincides with the ascending node. In this case, it looks to be almost 90 degrees, that the argument of periapsis, the perigee right here, is about 90 degrees away from the ascending node. So again, that tells you how that orbit is oriented like this. And then here's that reference direction in space. There's that arbitrary point that astronomers call the 0 point in the sky. And the right ascension, or the longitude of the ascending node, simply tells you the angle between that and where the ascending node is located in the sky. So you just measure that around, can be up to a full 360 degrees right there. So that is how you specify an orbit. And as I said, don't worry too much about the argument of periapsis and the longitude of the ascending node. They have more to do with the details of an orbit. The things you really need to understand that differentiate orbits are the size of the orbit, how big it is, its eccentricity, and its inclination. Those are sort of the three big ones. So a separate issue with satellites, or with these orbital elements, is to keep in mind that as an object orbits, the orbit remains constant, and the Earth rotates underneath it. So what I'm going to do here is I'm just going to switch this around a little bit so that we get a better view of this orbit of the Chandra X-ray Observatory here. And then I'm going to speed up time here. And as I speed up time, you will notice that the Earth is turning. It's going 1,000 times faster than real time here. And what you'll notice is that the orbit stays the same and the Earth rotates underneath the orbit. And it might actually be easier to see this if we do something like the International Space Station. So let me change all these again. And let's go back and look at the International Space Station for a second. Okay. So for the International Space Station, you'll remember that it was 1.066. See if I can get that in there. 1.07 is close enough for me being able to set these. The eccentricity is about 0. So I'm going to zoom in here. I'm going to pan out a little bit so you can see that better. The inclination of the International Space Station is actually about 51 degrees. So it's inclined by about 51 degrees right there. So that's the orbit of the International Space Station compared to the Earth. And what you'll notice is the space station is going round and round the Earth in this orbit, and the Earth is turning underneath it. Now, the space station goes around every 93 minutes. Remember, we calculated that in the last lecture. So it takes 93 minutes to go around. It takes the Earth 24 hours to turn around. But you can imagine that as the International Space Station is on this part of its orbit, they see some part of the world. And then 93 minutes later, by the time they come back around again, they're seeing a different part of the world because the world has rotated underneath the satellite. So keep in mind that an orbit does not, and this is really important, orbits do not rotate with the Earth. An orbit stays still in space while the Earth rotates underneath it. That's going to be really important to understand when we talk about polar orbits in a little while. So let's go ahead and put that aside for now. Just wanted to mention that before we move on to our next topic. All right, that's how we specify orbits in space. Now, how do we publish these orbits? That is, imagine that you wanted to track a satellite in space. How would you do this? Well, again, don't worry too much about the details of this. I want you to see this in case you ever do work with satellites and you want to know a little bit more about how we monitor their orbits. We publish their orbits as a set of numbers, and these numbers are given a very specific format. They're called two-line elements, or TLEs. And TLEs are a very compact way that you can publish the orbital elements for any Earth-orbiting satellite out there. And from those two-line elements, you can calculate exactly how the orbit is, what its shape is, what its inclination is, what its orientation is, and where the satellite is in that orbit. And you can download these two-line elements from lots of different sources, but the majority of people get them from the United States Strategic Command's Joint Space Operations Center. The Joint Space Operations Center, as we'll see here in a minute, operates huge radar, and they track all the objects in space that they can, and then they publish the two-line elements for these objects. And this is basically what the two-line elements look like. And again, don't worry about the details here. I'm not going to ask you to break them down in any detail. But basically, as the name implies, it's two lines of numbers. The numbers are separated by spaces, and each of the numbers has a purpose. So the first one right here is the catalog number. They basically catalog satellites, and there are a couple different cataloging schemes. And one of them is just basically a numbering scheme where we start with the very first launch and we work our way up, and every launch it's incremented by 1. So this is the 25,544th object right here. Turns out it's the International Space Station. So that's the catalog number for the space station. 98067A is also another catalog number. And by the way, the U here, I should mention, the U means that it's an unclassified satellite. So that means it's just a civilian satellite. So you're allowed to know the orbital elements of it. 98067A happens to be another international designator, another catalog number. It was launched, the first piece of the International Space Station was launched in 1998. And it was the 67th launch of the year, and the A means that it was the first part catalog from the launch. So sometimes a launch will have multiple parts. There'll be a satellite and an upper stage. There might be a satellite, an upper stage. The satellite might eject a cover. That cover gets a number as well. So there might be an A. The upper stage might be B. The cover might be C. In this case, we were launching a big piece of the International Space Station. That's the piece we're tracking. So in 1998, it was the 67th thing launched, and it was Object A. In this particular case, the orbital elements, 09 is the year, so this is from 2009, day 61.52440963. So you could convert that into a time. In fact, I downloaded the 2-line elements for the International Space Station today. When I recorded this lecture, 2021, on the 51st day. And so, as I said, the 25544 is the NORAD catalog number for the International Space Station. The U is, it's an unclassified satellite. The 98067A, COSPAR is the international organization that classifies and catalogs satellites. So 98 was the last 2 digits of the launch year. So it was launched in 1998. 067, it was the 67th launch that year. A, it was the first piece of the launch. The epoch year is in 2021. The day was day 51, which is Saturday, February 20th in 2021. And the time was 0.7160864 of a day, which corresponds to 17 hours, 11 minutes, 10 seconds universal time. The other numbers down here on the bottom, they specify the orbit. So the interesting numbers here down here, the 51.6445, that's the inclination of the orbit. So the International Space Station is inclined by about 51 degrees. The other important numbers are the right ascension of the ascending node is about 198.8 degrees. The eccentricity of the orbit is 0.0002926. The point here is not printed. It's assumed because all eccentricities have to be less than 1, so they all have to begin with a decimal point. So the decimal point is just assumed to be there. So it's 0.0002926. 35 degrees here, 0.2307, that's the argument of the perigee. The 72 is the mean anomaly where the satellite is in its orbit. And then the last one, down here, which is the one that tells you the size of the orbit. In these 2-line elements, for historical reasons, they don't give you the size of the orbit in kilometers or anything useful. They give it to you in the number of revolutions per day. So the number of revolutions per day for the International Space Station right now is 15.4898 on and on revolutions per day. That means the space station orbits the Earth 15.5 times every day. Or if you take the length of a day and divide by the 15 revolutions, you get a period of about 93 minutes, 92.96 minutes. Okay, so that's what the 2-line elements are. And again, don't worry, I don't want you to memorize what all these numbers are or how to decode one of these 2-line elements. I just want you to know what they look like, because they're a very, very common way of expressing satellite orbits. Now, if you would like to know when one of these satellites appears overhead, I highly recommend the website heavensabove.com. So heavensabove.com is a fantastic website for tracking satellites. They allow you to track all kinds of interesting things. So the first thing you'll notice when you log in, if you look in the upper right corner, it says that your location is unspecified, and it's got you at longitude 0, latitude 0. We don't want that. We need to change our observing location. So you can click on this button right here, and you can pick an observing location on the surface of the Earth. So they started you at 0 longitude and 0 latitude. So let's go ahead here and search for Charlottesville. So let's search and see what they come up with. So they come up with Charlottesville, Virginia. There we are. So there's our longitude and latitude. And I'm just going to say update and use that. So you'll see that user anonymous I'm in Charlottesville. Now, you can actually create an account for yourself, and I highly recommend that you do this because then you can store, the accounts are free. You can store many different locations there. So, for example, I have the exact longitude and latitude of McCormick Observatory remembered in here. So you'll see now it's coming up for Leander McCormick Observatory on the grounds of UVA, and I've got my exact longitude, latitude there. So you can look at, it shows you right now, this is the current position of the International Space Station over the Earth right there. You can actually get predictions of when the space station will be visible here in Charlottesville. So, for example, on the 20th of February, which is actually today, the day that I'm recording this, the International Space Station is passing overhead between 5:41 in the morning and 5:47 in the morning. Now, it's a great pass. It's going to get 54 degrees up in the sky. It's going to be a really nice pass. Problem is, I wasn't up at 5:40 this morning, so I missed this pass. You'll see that most of the passes right now, the way the orbit is oriented in space, most of the passes are occurring in the morning hours. You will see that there are times of the year when those passes occur in the evening hours, and then you get to see the space station in the evening. If you click on information about the orbit of the International Space Station, it'll show you the current orbit of the space station in a couple different views. This one is called the ground track, and then here are the two-line elements right there. So those are the two-line elements for the International Space Station, and here they are spelled out to help you figure out what the two-line elements are. But that's a little bit about how you find satellites. So it's a great hobby, by the way. I highly recommend it if you're interested in seeing satellites. Not only can you track the International Space Station, you can track all the new Starlink satellites that are being put into orbit. The X-37B is a U.S. Space Force mini space shuttle that's in orbit right now. The Hubble Space Telescope is not actually really visible from Charlottesville here. We're too far north. But then you can even get daily predictions for brighter satellites. And if you live in a dark area where you can see things that are fairly faint, you can see hundreds of satellites every evening. It's really quite remarkable how many satellites you can see up there. A lot of these that have R/B after the name, that means rocket body. So these are not actual satellites, but they're an upper stage that was used to place a satellite in orbit. So I recommend if you get the chance to go out to heavensabove.com and play with this to predict when the International Space Station will be overhead, when you might be able to see it. And by the way, I should have pointed out for a pass, if you click on the date right there, it'll actually show you a star map and it'll show you the path of the International Space Station across the sky. So that's another thing that you can get out of this. All right. Well, let's talk now about how it is that we actually measure an orbit. So we've talked about the orbital elements and what they mean. So how do we actually go out and physically measure the orbit of a satellite? I'll tell you the modern techniques. The old techniques were to actually observe the satellite at a couple different places in the sky on as many orbits as you could, and then you could do sophisticated calculations from that. Today, we actually primarily use radar for doing this. Now, one technique is to use a global positioning system that's on the satellite itself. Turns out a lot of satellites today have global positioning receivers mounted on them. And just like you can measure your longitude and latitude using GPS, they measure their longitude and latitude using GPS. They know the date and the time, and they can calculate their orbit based on that. So they just use GPS for determining their orbit. The primary way that we get the vast majority of orbital elements for things in space is with ground-based radar. What radar does is it sends a radio signal out into space. That radio signal hits the satellite, which is typically metallic. Metal is a good reflector, so those radio waves reflect back, and they come back to the radar. And what the radar can measure is the position of the object in the sky. What we mean by position is we mean its altitude, how high up it is, and its azimuth, which is the direction with respect to north. North would be an azimuth of 0. East would be an azimuth of 90. South would be an azimuth of 180. West would be an azimuth of 270. And then the altitude, how high up it is, or the elevation as it's often called, 0 degrees is on the horizon and 90 degrees is straight overhead. So the radar can tell you the position of the object in the sky, its elevation or altitude, its azimuth, how high up it is, what direction with respect to north. But because we're sending a radio wave out, and we know that radio waves travel at the speed of light, we can measure how long it takes the signal to get to the satellite, how long it takes that reflected signal to come back, and that allows us to measure the distance or the range to the object. So we know how far away it is, we know its position in the sky, and sometimes some radar will encode information in the signal that will allow you to determine the Doppler shift. That is, whether the object is coming towards you, away from you, and what its speed is towards you or away from you. With all of this information, you can plug them into sophisticated versions of Newton's modification of Kepler's law, and you can use that to then calculate the orbital parameters for your object. So that's how we do this. We typically use a radar station. You can also, if you don't have a radar and you're a satellite operator, since you're communicating with your satellite, you can actually send it a signal and measure how long it takes your signal to come back, and that gives you the range. And you can also measure the position of your satellite in the sky by looking at where the signal is strongest. So you point your antenna at your satellite where you think it is, and then as you track it across the sky, you move your satellite, your dish back and forth, your radar dish back and forth a little bit till you get the strongest signal, and then you get the position in the sky. And because you can send it information and measure how long it takes that information to come back, you can also get the distance. And then finally, the old-fashioned way is to just measure the position in the sky, but that takes a lot of observations then to measure the orbit. I want to talk a little bit more about this ground-based radar, though, and how we do that. The vast majority of orbital elements, as I mentioned, are measured by the United States Space Force with the Joint Space Operations Center. This is Eglin Air Force Base in Florida. And down at Eglin Air Force Base in Florida, there is a giant phased array radar. And that's what you're looking at here, is this phased array radar. What it does is it sends radio waves out into the atmosphere, out into space, and as pieces of satellites and rocket stages and pieces of debris pass through that radar beam, this radar can measure their altitude, their azimuth, their position, the distance to it, and in some cases can measure the speed, the velocity of this. And we have radar stations like this, a couple of them around the world. Another big one is Cavalier Air Force Station. It's the phased array radar in Cavalier, North Dakota. There are also primarily missile detecting sites up in Alaska and Greenland that are looking for ballistic missiles coming over the poles. They can sometimes measure orbital parameters, but these are the two primary radar stations that the Joint Space Operations Center uses for detecting material that's in orbit around the Earth. And you'll notice down there that little note that it tracks about 20,000 objects per day. So it measures the orbital elements for about 20,000 objects a day. So that's a little bit about orbital elements and how we measure those elements. Let's spend a few minutes now talking about the different kinds of orbits and what they're used for. So we're going to talk about the types of orbits. First of all, we're going to talk about orbits that are differentiated primarily by their inclination, and then we'll talk about orbits that are differentiated by the size of the orbit and why we would use different ones. So the first one, and probably the most common type of orbit, are equatorial and near equatorial orbits. And these are objects that are orbiting around the equator of the Earth or near the equator of the Earth. So this is an example of an object orbiting the Earth in an equatorial orbit. It's basically orbiting around the equator, or it's inclined only slightly to the equator. Those would be equatorial and near equatorial orbits. Polar orbits, on the other hand, go over, as the name implies, the poles of the Earth. So a polar orbit is a 90-degree orbit, or it has an inclination around 90 degrees. So instead of going around the equator, it's now orbiting around the poles of the Earth. And we'll see here in a minute why this is important. And then we've got prograde, which are satellites that are orbiting in the same way that the Earth rotates. And then we've got retrograde, which are orbits in the opposite direction from which the Earth rotates. These are inclinations between 0 and 90, and these are inclinations that are between 90 and 180. We'll talk about more about those in a second. But let's talk about these equatorial orbits for a second. So equatorial or near equatorial orbits, they have a low inclination or zero inclination. They're right over the equator in the case of an equatorial orbit. Now, the thing about these low inclination orbits is they can't see the whole Earth. Think about this orbit right here. Remember that the orbit stays still as the Earth rotates underneath it, which means this satellite passes over all parts of the Earth that are between this latitude on Earth and this latitude on Earth, because the Earth is going to rotate underneath it. So let me bring up here again that orbital mechanics website that I had up there a few minutes ago. And let's do the Hubble Space Telescope here. So for the Hubble Space Telescope, A is 1.08. So again, that's close enough right there. The eccentricity is tiny. It's 0.0002. I don't even think I can, I'll just 0.01 is probably as close as I can get to it there. And its inclination is about 28 degrees. So that's the orientation of the Hubble Space Telescope right there. That's the orbit that Hubble is in. If I speed up the Earth right here, you will see that Hubble, as it orbits around the Earth right here, as I change the true anomaly, you can see that that little red dot over here, that represents the satellite, and then at a true anomaly of 180 degrees, it's going to be down here at the bottom, and then as it comes around, you can see the satellite there with this little vector showing you its motion right there. So that's the satellite orbiting around the Earth. You'll see that it sees everything between a latitude of about 28 degrees north and a latitude of about 28 degrees south. But the Hubble Space Telescope never flies over the poles of the Earth. It never flies over Charlottesville. Here in Charlottesville, we're at 38 degrees north. The inclination of the Hubble Space Telescope is only 28 degrees, which means Hubble never flies straight overhead as seen here from Charlottesville. So the thing about low inclination orbits is that they don't see the whole planet. They only see the part of the planet that is between the lower inclination limit and the upper inclination limit. That is, you take their inclination, 28 degrees, so they see between a latitude of minus 28 degrees or 28 degrees south and 28 degrees north. If you really want to see the whole planet, you need to use a polar orbit. Because in a polar orbit, you change the inclination to be 90 degrees or close to 90 degrees. Now what happens is as your satellite orbits around the poles of the Earth and the Earth rotates underneath, your satellite at various times of the day will be over any part of the globe. And on every orbit, it'll be over the North Pole and the South Pole. But imagine that you want to study a point up high up in Alaska at least twice a day. It'll be underneath your orbit, once when you're going up and then once when you're coming down about 12 hours later. It'll be underneath that part of your orbit. So polar orbits have an inclination of about 90 degrees, and they have the advantage that they allow you to see the whole Earth as the Earth rotates underneath it. So here's an example of what a polar orbit looks like. To give you an example of an object in a polar orbit, let me make sure. Yeah, to give you an example of an object that's in a polar orbit, there are a number of amateur satellite trackers who track top secret classified satellites in space. And one of those is USA 245. USA 245 happens to be an optical imaging spy satellite operated by the U.S. Space Force. And it is the last of the Keyhole 11 optical reconnaissance satellites. So when we say an optical reconnaissance satellite, this is a spy satellite that you're thinking of, right? It looks like a giant telescope, but instead of pointing out into space, it's pointing down at the ground, and they're taking pictures of things on the ground, optical pictures of things on the ground. They probably also have infrared sensors as well as optical sensors. So its orbit is 0.0, in terms of size of the Earth's radius, 1.098. So it's about where I am right now. And its eccentricity is 0.05. So let's change this to 0.05. So there's the eccentricity. And its inclination is 97 degrees. So it's actually inclined a little bit more than straight over the poles. So that's what it looks like. Let's rotate this around so we can see it a little bit better and zoom out a bit. So that is the orbit of the USA 245, the KH-11 reconnaissance satellite as it orbits around the Earth. And you can see why it's in a polar orbit, because as the Earth turns underneath it, that means every point on the surface of the Earth passes under the orbit of this satellite twice a day. Now, one of those points is going to be on the night side of the Earth. Typically, one will be on the day side of the Earth. So depending on what you're trying to do, you're probably going to be taking most optical photographs during the daytime. Infrared work you can do day or night, but you'll see that as the Earth rotates underneath, and as you can imagine, probably one of the many large targets for this satellite is Russia. And you'll see now here that even regions that are very far north, in northern Siberia and in northern Europe, all of those are visible to this satellite because it's now orbiting over the poles. Unlike a satellite that orbits down around the equator like this, when all of those regions in the far north are invisible. Okay, so that's an example of a polar orbit. There's a particular kind of polar orbit that's called a sun-synchronous orbit. And a sun-synchronous orbit are polar orbits where the satellite passes over parts of the Earth at the same time of day. That is, the satellite always passes over the same areas at, say, 4 o'clock in the afternoon. And it turns out an inclination of about 98 degrees creates one of these sun-synchronous orbits. So what do I mean about the time of day? So imagine that this is the Earth, and the Earth, of course, is rotating. And in this picture, the Earth is rotating counterclockwise there. So this is an observer. There they are at sunrise. There's the middle of the day, noon. That's sunset, and this is midnight over here. So if this is noon, that's 1 p.m., 2 p.m., 3 p.m., 4 p.m., 5 p.m., 6 p.m. What we can have is a satellite orbit that's orbiting in such a way that it's always going over the, say, the 3 o'clock in the afternoon line. Now, the reason that you might want to do this, it's particularly valuable for land measurement satellites, so that when they're looking down at the ground, they're always looking down at the ground under the same lighting conditions, right? One of the problems you would have if your orbit was different than a sun-synchronous orbit is sometimes you'd be looking in the early morning when shadows are really long. Sometimes you'd be looking in around noon when things are casting their shortest shadows. The advantage to a sun-synchronous orbit is that you're always passing over the Earth at the same time of day. And what that means is that the same parts of the Earth always look the same because the lighting is always the same. So here's what a sun-synchronous orbit looks like. It's inclined 97 degrees. And what happens is as the Earth is rotating underneath the satellite is continuing in its orbit like this. And the Earth is rotating underneath it. But you'll notice, as seen from the sun, the satellite is always passing the equator in the same place. That is, the orbit is not moving around at all. Let me give you an example of when this is useful. NASA has in orbit right now a constellation of satellites called the A train, or the afternoon train. And they pass over the equator at about 1:30 p.m. local solar time. Now, the A train is a series of satellites that are used for monitoring the surface of the ocean, monitoring the atmosphere, monitoring the carbon content of our atmosphere. And the advantage to having all these satellites in the same orbit passing over the Earth at the same time is that we can compare the data from one satellite to another, so that if we see something interesting in one satellite, we can see what the other satellites saw with their instruments at the same time. So right now, the A train consists of 4 satellites, and they're in a 1:30 p.m. local solar time sun-synchronous orbit. And right now it consists of the Orbiting Carbon Observatory 2, which is measuring the amount of carbon dioxide in the atmosphere, because that's a major contributor to global warming. There's the Global Change Observation mission, Aqua, which is measuring ocean surfaces and winds over the oceans and the roughness of the surface of the ocean. There's the Aura mission, and then there were some past missions that are no longer operational. One that measured cloud cover, one that measured aerosols in the atmosphere, and the Parasol mission. So those are former satellites that are no longer functional. And by a 1:30 afternoon, I mean that this is the orbit of the satellite. So here's noon, here's 1 o'clock, here's 2 o'clock. So it passes over the equator at about 1:30 in the afternoon. And then as it passes over all these parts of Earth, it passes over them at exactly the same time every day. Now, sun-synchronous orbits are special because of that 97-degree inclination. See, the problem with a satellite orbit is because it's stationary, as the Earth orbits the sun, that stationary orbit will have different orientations with respect to the sun. This is kind of a hard figure to look at right here, but let's talk about this red line right here. So this red line represents a satellite, and it's a satellite in orbit around the Earth, and it's not in a sun-synchronous orbit. So here you can see that it's passing over, if the Earth is spinning this way with the pole here at the top, here you can see it's passing over the Earth at about 9 o'clock in the morning. Here you can see it's passing over this part of the Earth down here at about 3 a.m. So that's midnight right there. That's sunrise. That's about 3 a.m. Here it's doing it at about 9 o'clock in the evening, and there it's doing it about 3 o'clock in the afternoon. You'll see as the year goes on, as the Earth orbits the sun, the orientation of that orbit stays the same, which means the time of day that it's passing over different parts of the Earth changes as the Earth orbits the sun. A sun-synchronous orbit is special, and they're represented by this light-colored line. That 97-degree inclination means that orbit actually twists around, and we'll talk about in the next lecture why the orbit twists around. But that orbit twists around, and it twists around at exactly the same rate that the Earth orbits the sun, so that orbit always maintains the same orientation with respect to the sun, which means it's always passing over the Earth at the same times of day. So that's a bit of a complicated story, but just know that sun-synchronous satellites are really important for environmental monitoring and for imaging the surface of the Earth because they always see the parts of the Earth under the same lighting conditions. So here's an interesting question. Go out to the lecture exercises and answer this question. A rocket has to be traveling 7,660 meters per second to orbit the Earth. The rotation of the Earth can provide some of that speed. Which direction, if you're launching a satellite, which directions should you launch it to take maximum advantage of the rotation of the Earth? Should you launch it to the north, the south, the east, or the west? So go ahead and take a few seconds, go out to the lecture exercises and answer this question. If the Earth is rotating, and you have to think hard about which direction the Earth rotates, which direction should you launch your satellite to take maximum advantage of the rotation of the Earth? All right, what did you get for this one? Well, let's take a look at the rotation of the Earth. The Earth is spinning on its axis. That axis goes through the North Pole and the South Pole on the Earth. And as the Earth spins, you are being carried from west to east with the rotation of the Earth. In fact, if you're at mid-northern latitudes like I am right now, it's hard to believe, but if you're sitting still watching this lecture, you are actually moving about 800 miles an hour due east because of the rotation of the Earth. Every hour you go 800 miles further east. But you don't notice that rotation because not only are you moving 800 miles an hour east, but the building that you're in is moving 800 miles an hour east. The city that you're in is moving with you. The part of the country that you're in is moving with you. Even the air that you're breathing is moving at 800 miles an hour. And because everything is moving together, you don't notice that motion. Now, if you're standing at the North Pole, you're not actually moving. You're just turning around as the Earth turns. If you're down here on the equator, you have to make this huge big circle every day. Here at northern latitudes, we make a slightly smaller circle, and here in Charlottesville, we're moving about 1,300 kilometers an hour, or about 800 miles an hour, due east. Now remember, to be into orbit, you need to be orbiting at 7.66 kilometers per second, 7,660 meters per second. Turns out the rotation of the Earth can provide some of that. If you launch your rocket to the east, well, when you launch your rocket, it's already traveling 800 miles an hour for you. And that's a significant fraction of your orbital velocity. In the case of the space station, you'll remember its orbital velocity is 17,100 miles an hour. A free 800 miles an hour is a welcome addition to that orbital velocity. It allows you to launch larger components into space because the Earth is already giving you a push in the right direction. So now I want you to take a look at this picture and determine what latitude should a launch site be located to take maximum advantage of the rotation of the Earth. That is, if you want to take maximum advantage of the Earth's rotation, should your launch site be at the North Pole, Should it be on the Arctic Circle? Should it be about the latitude of central Florida, 28 degrees north? Should it be on the Tropic of Cancer, which is about 23 degrees north? Or should it be on the equator? What do you think? So take a look at this image and answer that question. Where should I put my launch facility to take maximum advantage of the rotation of the Earth? All right, what do you think on this one? Well, the answer on this one is that you want the maximum speed. And if you look at the speed here at different latitudes on Earth, you'll see that the North Pole is definitely not a good place to launch satellites from because you're only spinning in a circle. You're not actually moving at all. The further south you go till you get to the equator, the speed increases. People on the equator, they have to make this huge, big circle, and they have to do it in 24 hours. People up here in the far north, they have to make the same circle, but their circle's a lot smaller, but they have to do it in the same 24 hours, so their speed is much slower. They're moving about 830 kilometers an hour. Down here at the equator, they're moving twice as fast at 1,650 kilometers per hour. So the best place to launch satellites would be on the Earth's equator, because then you get the maximum advantage of using the Earth's rotation. Now, you might say, well, why didn't the United States build their launch facilities on the equator? And, well, that comes down to national security. When the United States was building its first launch facilities, it was the height of the Cold War. The United States decided that even though there is an advantage to building launch facilities on the equator, there was a greater national security advantage to keeping those launch facilities in the continental United States. So in the case of Cape Canaveral, they moved the launch site as far south as they could. So that's why it's in Florida, to take maximum advantage of the rotation of the Earth. The further south you are, the faster you're going. Now, the European Space Agency, they didn't have the same national security concerns, and so the European Space Agency built their launch facility on the east coast of South America in French Guiana. And so they operate a large launch site in French Guiana down right there in South America, and they are located right on the equator. And so for a given size rocket, they can launch a slightly heavier payload to orbit because they're moving a little bit faster than they would be in Florida. They're moving a lot faster than they would be in Europe because Europe is so far north. Now, there are companies that try and take advantage of this. A company called Sea Launch was doing this. Sea Launch took an old oil platform and converted it into a mobile launch pad. And it was actually stationed in Los Angeles, California. But they would sail this down to the equator and they would launch rockets from the equator because that would allow them to put the maximum payload into orbit. There were two ships that would go down. One was the oil platform. Was brought down by, it was essentially a giant barge and brought down there, stabilized. And then there was another ship that would join it, and the ship contained the control systems to launch the rocket and the rocket itself. The two of them, they would unload the rocket from the second ship through this hangar door right here into this facility where they would prep the rocket for launch, move it out of the launch pad, and then launch from the equator. So unfortunately, Sea Launch went bankrupt, and it's unclear what Sea Launch's future is right now. So what about retrograde orbits? If it always is to your advantage to launch to the east, is there ever any advantage to launching to the west? And the answer to that is generally no. Retrograde orbits are backwards orbits. They are where you launch from the east towards the west. Now, this is a huge penalty for doing this because remember, if you launch to the east, you get a free 800 miles an hour. If you launch towards the west, you have to overcome that 800 miles an hour. So the first acceleration that you do of your rocket to get from 0 to 800 miles an hour is just to cancel the rotation of the Earth. And then you still need to gain the 17,100 miles an hour on top of that it takes to get to orbit. So there's a tremendous penalty to be paid for launching to the west. So why would you ever do it? The only country that has really done this is Israel. Israel has launched 5 Shavit satellites into retrograde orbits, and they do this because if you imagine where Israel is located on the eastern shore of the Mediterranean Sea, if they were to try and launch towards the east, they would be launching out over Syria, Jordan, Iraq, Saudi Arabia, Iran, All of these countries are unfriendly to Israel, so Israel generally launches their satellites to the west, out over the Mediterranean Sea, but that does impose a tremendous penalty for doing that. So that's a little bit about orbits and their changing inclinations and why we might give a satellite a particular orbital inclination. Let's talk about orbital regimes now, altitudes above the surface of the Earth. And typically we divide these orbital regimes into three main areas: low Earth, mid Earth, and high Earth orbits. And then there's also the very special case of geosynchronous and geostationary orbits. And we'll talk about those at the very end. So let's talk a little bit about and I did want to mention on these where these are located on a globe of the Earth. So if I have my standard 12-inch globe of the Earth right here, a low Earth orbit would be a tiny fraction of an inch above the globe, and a mid-Earth orbit would be anywhere from about 2 inches to about 30 inches or so above the globe, where we have geostationary satellites, and then the high Earth orbits would be above that. Here's another picture of them. So you can see the Earth right there. The low Earth orbit is very close to the Earth. The mid-Earth stretches quite far out, and then the high Earth orbit, geosynchronous, and the high Earth orbit is higher than that. And there's the moon way out there at the very edge. So let's talk about low Earth orbit to begin with. So low Earth orbit is this orbital regime that's very close to the Earth, and it is by far the most populated area of satellites around the Earth, both satellites and space debris around the Earth. In fact, here's a map. It's going to take it a minute or two to load here, so I'll give it a second to load up and while I talk about it. But this is a map of all the satellites in orbit right now. So this is 19,253 satellites that they downloaded from the NORAD catalog of satellites of objects. And you can see here that the vast majority of objects are in low Earth orbit. In fact, if I just zoom in here, you can just see the vast number of satellites, rocket bodies, debris. I mean, what you're looking at here are not all operational satellites. You're looking about half of them are going to be rocket bodies. These are upper stages that were used to launch a satellite. And then once the satellite is released, today we try and bring those upper stages down so they don't create space debris. That's not always possible. In the past, we certainly did not have that practice. So there are thousands of rocket bodies up there. And then, of course, there are tens of thousands of pieces of space debris. Low Earth orbit are typically orbits that have an altitude of less than 2,000 kilometers. And so that means that their orbital periods are anywhere from about 88 to 127 minutes. So from an hour and a half to about 2 hours. And this is where the vast majority of satellites are located in low Earth orbit. So what are some examples of low Earth orbiting satellites? Well, there's all kinds of satellites in low Earth orbit. There's lots of Earth imaging satellites in low Earth orbit. So these include the Landsat series. Landsat are a series of Earth imaging satellites. They are a corporation, but they are a corporation that was founded by a number of countries in order to provide Earth imaging. So farmers can use Landsat images, land planners, all kinds of people use images of the Earth taken by Landsat. Now, in addition to Landsat, there are a lot of private companies that have launched their own satellites to do photography of this or imaging of the surface of the Earth, or photography of the surface of the Earth. And so if you have a particular need, you can go to one of these companies and purchase an image of the area of the Earth that you want. So Iconos, GeoEye, Digital Globe, Spot Image, there's all kinds of these private companies out there that are doing this right now. So that's one example of low Earth orbit. And the obvious thing is here, Earth imaging satellites want to be in a low orbit because then they are closest to the surface of the Earth, which allows them to see the most detail. Another use for low Earth orbit are weather satellites. Right now, the National Oceanographic and Atmospheric Administration has their Polar Orbiting Operational Environmental Satellites up there, or POES satellites. So I'm bringing up here a little animation that shows you the ones that are operating right now. But these are the weather satellites. These are the low Earth orbiting weather satellites. We also have, as we're going to find out later on, weather satellites that are further out, but these are the low Earth ones. These are the ones that provide us the most detail of what the clouds look like. And they not only measure, obviously, cloud cover on the Earth, but they can measure things like precipitation and wind speed and other things. So that is a little bit about the POES satellites. So another use is weather satellites. Obviously, low Earth orbit is used for surveillance satellites. We've talked already about the optical spy satellites that are taking pictures of the Earth. There are also spy satellites that use synthetic aperture radar. This is where the satellite bounces radar waves off the surface, and this allows nations to see through cloud cover. For example, it would be very difficult if someone built a military base in an area that's often covered in clouds. Your optical imaging satellite couldn't see what's below the clouds. So a synthetic aperture radar satellite allows you to bounce radar waves off the surface, and those radar waves, allow you to determine what's down on the surface, and you can measure the not only where things are, but you can actually measure how things move using synthetic aperture radar. Signal intelligence satellites are satellites that are bristling with antennas, and they're listening for all kinds of analog and digital communications. So, of course, a significant part of any military organization is communicating with soldiers in the field, communicating with other units, and the goal here is to try and spy on all of those military and government and even commercial communications. And so there are signal intelligence satellites that are flying overhead that are picking up all the radio waves. When you think about the radio waves that your cell phone is emitting, for example, they can pick up transmitters that are stronger than your cell phone and pick up all those radio waves. Low Earth orbit is used for science satellites. The Hubble Space Telescope is in low Earth orbit. The goal for the Hubble Space Telescope was to get it outside of the Earth's atmosphere for two reasons. The first one is that the Earth's atmosphere blocks particularly kinds of light that Hubble wanted to see, like infrared light and ultraviolet light. And the only way to see ultraviolet and infrared light was to get the satellite out of the Earth's atmosphere, because the Earth's atmosphere absorbed that light. Telescopes here on the ground can't see it because it gets absorbed by our atmosphere. The other reason for putting the Hubble Space Telescope in orbit was to get it above the blurring effects of the Earth's atmosphere, which is why it takes such crisp, clear images. But Hubble is only orbiting a little bit more than 400 miles above the surface of the Earth. And so Hubble is not any closer to the distant stars than we are down here on the surface. The goal for Hubble, putting it in space, was not to get it closer to the distant objects. It's only 400 miles above the surface. The whole goal for Hubble was to get outside the Earth's atmosphere. Now, you might think that there's an advantage to putting it at least a little farther away from the Earth. Why put it at 400 miles? Why not put it at 4,000 miles, get it a little further away from the Earth? And there is some advantage to that. But remember, the Hubble Space Telescope was meant to be serviced by astronauts. So in order to be serviced by astronauts, it had to be in a low Earth orbit. It had to be low enough that the space shuttle could get to it. And in fact, the deployment of the Hubble Space Telescope was the highest that the space shuttle ever flew. And the missions to service the Hubble Space Telescope are also some of the highest missions that the space shuttle ever flew in its history. And then last but not least, there's a lot of communication satellites that are used in low Earth orbit. Probably the two primary ones that are commonly talked about today are the Iridium satellites. Iridium is a constellation of communication satellites that pick up a satellite phone. So you can buy a phone that's just a little bit bigger than your cell phone, and there's a constellation of Iridium satellites, and they're staring down at the surface of the Earth, and every spot on the surface of the Earth is covered by at least one of these Iridium satellites, and you can use this satellite phone to place a call from anywhere on Earth. Your call goes up to the Iridium satellite, it gets transferred over to another satellite, then down to the ground, and then it gets routed through landlines, through regular lines down on the ground as much as they can. But you can be in the middle of the South Pacific, or you could be in Antarctica, or you could be in the remote Amazon and get good coverage with one of these Iridium satellite phones. Now, another use of these is the Starlink system that we've already seen. Starlink is SpaceX's attempt to build an internet provider. And this internet provider is going to use a series of ultimately what will be about 12,000 satellites or so orbiting around the Earth. Each of those satellites are communicating with a little base station that you're going to have here on the Earth. Be a little dish about this big or so that you're going to mount on top of your house Or if you're out in the field, you'll just bring it with you, and that little dish will talk to one of the Starlink satellites. And the Starlink satellites, there's going to be at least 3 orbits. There's going to be a low orbiting plane, a mid orbiting plane, and then these polar ones here. You'll notice that the polar region is not covered nearly as much because SpaceX does not see the need for high-speed internet over the poles very much. They see it mostly at the northern latitudes here. So that's why between the northern latitudes and the far southern latitudes, but they don't see much need for the coverage over the poles. And so there will be some polar orbiting satellites, but most of them will be in the have inclinations of up around 60 degrees or so, roughly. So anyhow, that's another example of low Earth orbit satellites. Okay, what's disadvantage to low Earth orbit? Well, the primary disadvantage to low Earth orbit is atmospheric drag. That is, in low Earth orbit, you are still in the outer reaches of the Earth's atmosphere. An important thing to realize about the Earth's atmosphere is as you get higher and higher, the atmosphere gets thinner and thinner. But there's no place that the atmosphere ends. For historic purposes and for contest purposes, we have a line that's at about 100 kilometers altitude. That's about 62 miles altitude. And some people will say that if you go above that line, you get your astronaut wings because we define that as the edge of space. And that's fine. They just had to draw a line somewhere, so they arbitrarily drew it at a nice round 100 kilometers or 62 miles. But the thing to know is that there's still plenty of atmosphere there. And in fact, satellites cannot orbit the Earth at an altitude of 100 kilometers. There's so much atmospheric drag that they'll be dragged down right away. A really good example of atmospheric drag is the space station. This is a plot of the International Space Station's altitude as a function of time. And you've probably heard me mention a couple times now that the International Space Station is typically up around 420 kilometers above the surface of the Earth. But if you watch its altitude over time, you'll notice that its altitude is slowly decreasing. And what you see here is atmospheric drag. Even up where the space station is, at an altitude of 420 kilometers, roughly about 250 miles, there's still enough atmosphere that as this space station, the size of a football field, plows through the atmosphere, the plowing through the atmosphere slows it down enough that it slowly falls over time. Now, as it's slowly falling over time, we will reboost its orbit on regular occasions. And so they will use either one of the Russian Progress resupply vehicles, or they can use thrusters that are located on the Russian Zarya segment of the International Space Station, and they can fire those thrusters and boost the orbit. But then atmospheric drag takes over and starts bringing it down again. And then they can boost the orbit again. And then atmospheric drag starts bringing it down. And for various reasons, sometimes they have to lower the orbit of the International Space Station. There were lots of things going on. You'll see that this is 2020. There were lots of things going on this year, various missions, including the SpaceX Crew Dragon mission. So they were doing a fair bit of changing the altitude of the space station over time. But you'll notice that when they're not doing anything, it's just slowly falling over time, and then they boost it and it slowly falls over time. All right. So another disadvantage of low Earth orbit is space debris. Space debris are small chunks of either spent, well, they can be active satellites, they can be spent rocket stages, they can be dead satellites that are no longer operational, or they can be pieces of satellites that have broken off satellites. We've had satellites accidentally explode. A lot of satellites have accidentally exploded at the end of their lives. And that creates, instead of one big satellite orbiting the Earth, you now have hundreds of pieces of debris that you have to track. There have been a couple famous cases. One about 10 years ago where China used an anti-satellite weapon to destroy one of their own satellites and created thousands of pieces of space debris. We've had a couple incidences in history where two satellites have collided with one another, destroyed the satellites, and created thousands of pieces of space debris. So another disadvantage of low Earth orbit is just the tremendous amount of debris that is out there, a phenomenal amount of debris. And the thing to keep in mind is, you'll remember from the homework assignment, this debris carries with it a tremendous amount of energy, right? Even something that's as small as a grain of sand is traveling much, much faster than a bullet. And something the size of a grain of sand can contain more energy than a bullet contains because of its fast motion. Remember that the kinetic energy of something goes as 1/2 times the mass times the velocity squared. So if it's going, say, 10 times faster than a bullet, its energy, would be 100 times greater. So even small pieces of debris, like little flecks of paint and little tiny pieces of aluminum, they become very dangerous projectiles in low Earth orbit. The International Space Station is designed to survive a strike of something that's about 1 centimeter by 1 centimeter by 1 centimeter in size. Something bigger than 1 by 1 by 1 centimeter in size has the potential to destroy the International Space Station, or at least create a leak large enough that the astronauts would have to abandon the space station. They couldn't stay on board. What's interesting is the smallest things that we can track with radar are about 4 centimeters by 4 centimeters by 4 centimeters. So it turns out we cannot track the small stuff, even the small stuff that could doom the International Space Station. We can't track it. We can only track things that are bigger than that. Typically, an object has to be about 4 inches by 4 inches by 4 inches in size, or about 10 by 10 by 10 centimeters in size, in order for us to track it. For some objects, we can do it when they're a little bit smaller, but for the really small stuff, which is still dangerous, we can't even track that with our radar. So space debris is an issue for low Earth orbit. And it's important to know that all human spaceflight, except for the Apollo missions to the moon, all human spaceflight has been in low Earth orbit. Okay. What about medium Earth orbit? Medium Earth orbits have altitudes between 2,000 kilometers and 35,786 kilometers above the surface, and their periods are typically 2 to 12 hours or so. The problem with medium Earth orbits is that it's a very difficult radiation environment. You're in the Van Allen radiation belts a lot of the time, and we'll talk more about those Van Allen radiation belts here in a second. So why would you put a satellite here? The primary use for these mid-Earth orbits are navigation satellites. This is where the global positioning satellites are located. The Russian system, which is similar to global positioning, the U.S. global positioning system, is called GLONASS. And the Europeans have their own global positioning system called Galileo. And all of these satellites are located in mid-Earth, medium Earth orbits. There are some communication satellites here. The Molniya satellites, which are a Russian series of satellites, are in these mid-Earth orbits, and they are used for communications. And then there's some space environment science. If you're interested in studying the radiation belts around the Earth, you would obviously be in a mid-Earth environment, because that's where you're inside the radiation belts around the Earth. All right, so let's take a look at the motion of these satellites. All right, so here are satellites at different orbits. So the first thing you should notice is Kepler's third law of planetary motion, right? Look at the satellites that are very close to the Earth. The satellites here that are in low Earth orbits, they're moving very, very fast compared to the satellites that are in mid-Earth orbits, compared to the satellites that are up there in geostationary Earth orbit. So the first thing you'll notice here is the difference in the orbital speeds. You'll notice also that there's a big gap. There's a lot of satellites in low Earth orbit down here. There are not many satellites in between. And then there's this ring of satellites that are in the mid-Earth orbit right there. And then we'll talk about the geostationary ones after that. So let's use as an example of this the Global Positioning System. So the Global Positioning System satellites, GPS, consists of about at least 24 satellites. Currently, as I'm doing this in February of 2021, there are 31 operational GPS satellites, but the constellation requires a minimum of 24. There are 6 orbital planes, and there are at least four satellites in each orbital plane. So an orbital plane is an orbit like this, and there will be 4 satellites pretty evenly spaced around the orbital plane like that, and then there are 6 of these planes around the Earth. And the goal is, wherever you are, anywhere on the surface of the Earth, that at least 4 of these satellites will be high up in your sky at any one time, because you have to use the positions of 4 satellites in the sky to triangulate your position on the surface of the Earth. Now, we don't have the time to get into how GPS works. Just very quickly, though, there's an atomic clock on board the satellites. They send that time down to your little receiver. Your receiver notes that all 4 clocks do not agree, and they don't agree because that one might be further away. This one might be a little bit closer. This one might be really close to you, and so the close signal gets to you faster. The really far clock takes longer for the signal to get to you. So the delay in the timing of the signal tells you how far away the satellite is from you. And then the satellite is also broadcasting its orbital parameters. And so your little receiver calculates where that satellite is in space, calculates the distance to that satellite, and it does this for 4 of them, and using that information, it can triangulate your location anywhere on the surface of the Earth. The more satellites you can see, the more accurate your location is, but you need at least 4 satellites to measure your location. And those satellites are located about 20,000 kilometers above the surface of the Earth. In fact, their orbital period is exactly half of a day. So it's 12-hour orbits that they're in. Now, as I mentioned, a difficult thing about this mid-Earth orbit is the fact that you are constantly in the radiation belts. There are 2 sets of radiation belts around the Earth called the Van Allen belts, and they were discovered actually with the Explorer 1 mission. The very first satellite that the United States launched made a major discovery that the Earth is surrounded by these radiation belts. There's the inner Van Allen belt and the outer Van Allen belt. They're named for Van Allen, the scientists who helped build the Explorer 1 satellite. The inner belt is about 1 to 12,000 kilometers above the surface. The outer belt is 13 to 60,000 kilometers above the surface. And what we mean by radiation belts is these are places where charged particles from the sun, as the sun is giving off a wind of charged particles. And as these charged particles encounter the Earth's magnetic field, they can get trapped in the Earth's magnetic field. And in particular, they can get trapped in these 2 radiation belts. So these belts have a large number of high energy charged particles. And those high energy charged particles, well, that's radiation, at least one form of radiation. And operating your satellite in these radiation belts can be a difficult environment. After all, over time, that radiation exposure can degrade your electronics and can degrade cameras. It can degrade the performance of solar arrays. Over time, this radiation damage does damage to your satellite. Now, it's generally not a problem for humans because, except for the Apollo missions, humans are down here very close to the surface of the Earth, right? All human missions except the Apollo missions were in low Earth orbit. They were well below the lower limit of the inner Van Allen radiation belt. So our astronauts in the International Space Station don't have to worry about the Van Allen belts. In the case of the Apollo astronauts going to the moon, the Van Allen belts were a significant source of radiation exposure, but the advantage is that you're traveling through them and you're doing it fairly quickly. You're right after launch from Earth, so you're traveling fairly fast, and so you get through the radiation belts in very little time. So although they have a high radiation environment, you're going through them quickly, so your overall radiation exposure is fairly low. So that's a little bit about the danger of operating in mid-Earth orbits. Now, the next orbital class that we're going to talk about are geosynchronous orbits. Geosynchronous orbits have an orbital period of 23 hours, 56 minutes, and 4 seconds, which is the length of time that it takes the Earth to turn on its axis with respect to the distant stars. Now, you might say, wait a second, it's 24 hours, isn't it? 24 hours is how long it takes the Earth to turn with respect to the sun. But with respect to the stars, the Earth turns in 23 hours, 56 minutes, and 4 seconds. The difference between the two comes from the fact that the Earth is also orbiting the sun. And if we see the sun today, tomorrow when we're over here, the Earth has to rotate a little bit longer to get the sun to come back. And so the Earth has to rotate an extra 3 minutes and 56 seconds every day for the sun to come back to noon. So the actual rotation period of the Earth is 23 hours, 56 minutes, and 4 seconds. So imagine that we launch a satellite into an orbit that's far enough away from the Earth that its orbital period is 23 hours, 56 minutes, and 4 seconds. That means that as the Earth turns on its axis, the satellite orbits the Earth at the same rate, and the satellite does not appear to move as seen from the Earth. The satellite appears fixed above a given longitude. And this was first discovered by first promoted by the science fiction author Arthur C. Clarke. Arthur C. Clarke proposed in a paper years ago that we could launch a series of communication satellites into this orbit, and that these communication satellites, by putting 3 of them in orbit around the Earth, would provide continuous coverage around the Earth. And so sometimes the geosynchronous belt is called the Clarke belt. So the question I have for you is, how high up is the geosynchronous orbit belt? So I want you to answer this question. What is the semi-major axis of an orbit with a period of 86,164 seconds? If you're curious, that's 23 hours, 56 minutes, and 4 seconds. So I want you to use Kepler's third law as modified by Newton. Plug in the period of 86,164 seconds and calculate the semi-major axis in kilometers. So stop the lecture, go out, do the lecture exercise, and then come back. All right, welcome back. So what did you get for this one? Let's do the calculation. In order to have the semi-major axis of an orbit with a period of 86,164 seconds, well, we use Kepler's laws modified by Newton. The semi-major axis cubed, I really should have put an a cubed in there, but the semi-major axis cubed is gm over 4 pi squared times the period squared. Well, g is our old friend, the gravitational constant, 6.64 times 10 to the minus 11th. M is the mass of the Earth, since we're orbiting the Earth, 5.972 times 10 to the 24th kilograms. 4 pi squared, just constants down there, times the period, 86,164 seconds. Plug all of those numbers into your calculator and you come up with a semi-major axis cubed of 7.496 times 10 to the 22 meters. Take the cube root of that. Don't forget to take the cube root of that. Make sure that you understand how to take the cube root on your calculator. You'll need that on the quiz. You come up with 4.216 times 10 to the 7th meters, or 42,164 kilometers. That is the radius of an orbit, which takes exactly one Earth rotation. The period of it is the same period that the Earth rotates. And you'll often hear the geostationary belt referred to as being 35,786 kilometers above the Earth's equator. So this is the distance from the center of the Earth. That's the semi-major axis that we need to use in our equations, but we'll often talk about it as if it's above the surface of the Earth, and so it's 35,786 kilometers from the surface of the Earth. Here's what we mean by a geosynchronous orbit. The Earth spins once every 23 hours, 56 minutes, and as the Earth spins in 23 hours, 56 minutes, the satellite orbits in 23 hours, 56 minutes, and 4 seconds, and so the satellite appears to sit still above a given location on the surface of the Earth. And this was Arthur C. Clarke's idea of putting 3 satellites in orbit around the Earth. And those 3 satellites would each look at 1/3 of the Earth. And then those satellites, you could get a radio broadcast from, say, North America, go up to the satellite, be sent over to this satellite, and then back down to the Earth in Europe. And so you could use this to communicate from North America to Europe. Today, of course, we use the internet. A lot of internet traffic does go through satellites today. A lot more of it goes through undersea fiber optic cables, but in any case, some of the internet traffic today goes, well, I shouldn't say some, a lot of it goes through satellites, where you broadcast from the Earth up to the satellite and back down to the Earth again. So, and that was first published in October of 1945. Now, the thing about Arthur C. Clarke is he didn't imagine robotic spacecraft like we have today. He actually imagined 3 orbiting space stations that were crewed by human beings. The human beings would be up there to maintain the electronics and maintain things. So he actually called them 3 space stations as opposed to 3 satellites. Today, of course, putting space stations up there and staffing it with a crew would be extraordinarily expensive. So we use robotic spacecraft to do it instead. So that is a geosynchronous orbit. There is also a geostationary orbit, and geostationary and geosynchronous orbits are about the same thing with one minor hook, which is that a geostationary orbit has an inclination of 0 degrees and an eccentricity of 0 degrees. That is, you can be in a geosynchronous orbit and still be tilted with respect to the Earth's equator and have an eccentricity that's not exactly 0, but a geostationary orbit tries to have an eccentricity as close to 0 as possible, and it tries to have an orbital inclination of 0 degrees. And the reason for that is that in a geostationary orbit, the satellite appears to sit perfectly still from the surface of the Earth. And then you can take your antenna and you can aim your antenna at it, and you never have to move your antenna again. So for those of you that have ever seen a dish network dish, right, that's what's happening with Dish Network. There is, in this geostationary belt up there around the Earth, there are hundreds of satellites in this geostationary belt. And because they have 0 inclination, they're directly above the equator. Because they have 0 eccentricity and an orbital period of 23 hours, 56 minutes, 4 seconds, they appear to sit still in the sky. You can take your Dish Network dish and you can aim it at the satellite that's broadcasting your Dish Network, and you never have to move the dish again. So that's the great advantage to geostationary satellites, is you don't have to move the dish around. Now, any given geostationary satellite can see about 42% of the Earth. They can't see the polar regions. In fact, they can't see anything with a latitude that's greater than 81 degrees. They can only see things that have a latitude that's 81 degrees or less, and they can see about 42% of the Earth at one time. So but that's the sort of the field of view, the broadcast field of view for a geostationary satellite up there. Okay, and they're very commonly used. This is just a list of some of the geostationary satellites that are in use right now up there in orbit. Let me give you go back to this animation that I had up here a few minutes ago. Let's see, it was this one that I wanted to do. If I zoom out, the geostationary belt is pretty obvious in this view right here. You will see all these satellites right here in this geostationary belt. So they're right above the Earth's equator. You can see it's a very, very crowded region of space. Now, it takes a lot of fuel to get these satellites up here to geostationary orbit. When they are done with their lifetimes, when their life is over, we don't have enough fuel to bring them back to Earth or to have them burn up in the Earth's atmosphere. So just beyond the geostationary belt is what's called the graveyard orbit. And so the goal for these operators is when one of these satellites is getting close to running out of fuel, when it's getting close to the end of its life, they will actually use the last remaining fuel to boost it to a higher orbit, and that's the graveyard orbit. It gets it out of the way of the other satellites and ensures that it won't interfere with the rest of the geostationary belt. So that is geosynchronous and geostationary satellites. There are a couple of specialty orbits. One of them is the Molniya orbits that the Russians developed. The problem that they had with geostationary satellites is there are large portions of Russia and the former Soviet Union, when this was first developed, that are at or above 81 degrees north. That is, these north polar regions are not well served by a geostationary satellite. So to serve those northern regions, they developed a highly elliptical orbit called a Molniya orbit that comes very close to the Earth and then comes out. It's tilted at a very high inclination so that the satellite goes quite high above the Earth. But and they have a period of 12 hours. The inclination is 63 degrees. Period of 12 hours. But you'll notice here that they spend, that's 11 hours, 12 hours, 1 hour right there. You'll notice that they whip around the Earth thanks to Kepler's second law, and they spend a lot of time up here at their perigee, their apogee, their point furthest from the Earth. So they spend a lot of time up here at apogee. And so they're great communications satellites because they're high up above the northern latitudes. So they're high up above you, and they're moving slowly up there. So they have excellent visibility in the far north. Another similar orbit to this is one that's called the Tundra orbit. The Tundra orbit is used by Sirius Satellite Radio. It's where the Molniya orbits had an orbital period of 12 hours. These have an orbital period of 24 hours. And if we look at the ground track for these satellites, that is the track that they make on the surface of the Earth, you'll see that they spend a lot of their time hovering over North America. You'll notice that when they come down here, watch Sirius 3, it's going to whip around the bottom of the Earth and come back up quickly, because in the southern hemisphere, they're close to the Earth, so they whip around very quickly. And then as they pull away from the Earth, they do it at very high latitude. So they're going very slowly above North America here. And they're broadcasting Sirius Radio down to us, for those that have a subscription to Sirius Radio. All right. The last one are high Earth orbits, and these are altitudes above the geostationary belt, and these are very rarely used. These are periods that are longer than 24 hours. And the primary use for these orbits are things like science satellites. So the Chandra X-ray Observatory, which is a major X-ray observatory built by NASA, operated by NASA. The problem with the Chandra X-ray Observatory in low Earth orbit and medium Earth orbit is the radiation environment. So to have long periods of time where it was away from the Earth, out of the radiation belts, they launched it on a highly elliptical orbit. Here's a picture of the Chandra X-ray Observatory's orbit compared to the orbit of the moon. And you can see that it goes about a third of the way out to the moon there. And again, because of the way it orbits, it goes very quickly around the Earth, so it doesn't spend much time down here in the radiation belts, and it spends a long period of time up here when it is at apogee. So it's going very, very slowly, spends a long time up here far from the Earth where they do all the observations. Then they turn most of the instruments off as it whips around the Earth, and it does it again. So that is the Chandra X-ray Observatory. The last thing I'll mention in this lecture are ground tracks. I've shown you some pictures here of what the track of a satellite looks like across the surface of the Earth. So the thing to keep in mind is that the Earth is constantly turning underneath the satellite. So if we have a satellite in an orbit, in an inclined orbit like this, the satellite's orbit stays the same, but the Earth is rotating underneath it. And what that means is if we were to draw the track of this orbit on the surface of the Earth, it would look like a sine curve like that. You'll remember back from high school geometry what a sine looks like. It looks like this curve like this. But that curve is constantly shifting across the surface of the Earth because the Earth is rotating underneath it. So the ground track shifts westward, shifts to the west, and every orbit because the Earth is turning underneath the satellite. So let's imagine, say, the Hubble Space Telescope here, which is inclined at an angle of 28.5 degrees. What its current orbit looks like is this middle track right here. So its current orbit is this middle track right there. This was its previous orbit, and then this is its next orbit down here. So you will often see diagrams like this that show the orbital track of a satellite over the surface of the Earth. So what it's showing you is there's the Hubble Space Telescope right now. So at this moment in time, it's over the Western Pacific, just south of Japan, just northeast of the Philippines there. That's where the Hubble Space Telescope is at the moment that this picture was taken. And then it will continue in its orbit, and then its next orbit will be this track right here, which will be a little bit further to the west. And it's further to the west because the Earth is rotating underneath it. So why do we make tracks like this? Well, we make plots like this because they help us determine when we can see and talk to a satellite. So typically for a satellite like the Hubble Space Telescope or the International Space Station, they can see a certain portion of the surface of the Earth, right? Unlike a geostationary satellite, which is far away and can see 42% of the Earth, the International Space Station and the Space Shuttle and other things in low Earth orbit, when they look down at the Earth, they see much less than 42% of the Earth. In fact, they might only see a tiny fraction of the surface of the Earth. And from the surface of the Earth, when we look up at them, we only see them for about 8 minutes or so as they go across the sky. So these ground tracks can be used with ground stations to determine when we can contact the International Space Station. So for example, this yellow circle right here is for a ground station right there. And what that means is that when the space shuttle or the space station is inside that yellow circle, we can communicate with it. Because the space station, or we'll say the space station in this case, the space station is above the horizon as seen from that ground station. On the other hand, the space shuttle and the space station, this is right before they dock together. So this white circle is the part of the ground that the space shuttle can see. This white circle is the part of the ground that the space station can see. And so they can't communicate with this ground station until they are within, until that ground station is within their white circles right there. And you can see a variety here of different ground stations. These are some of the Russian ground stations that are used for contacting the International Space Station. So that's a little bit about how ground tracks are used and what they look like on a map. All right, this finishes part 2 of lecture 4. In the next lecture, we're going to see why orbits change. Orbits can modify and change over time. Besides intentionally changing the orbit, there are perturbations, things that push and pull on the orbit of a satellite that cause those orbits to change over time. And we will see that in part 3 of lecture 4. I will see you then.